Hi, I'm Aaquib Tabrez.
And I'm Matt Luebbers, and we're from the Cairo Lab at the University of Colorado Boulder with Professor Brad Hayes, and we'll be talking about our paper on descriptive and prescriptive visual guidance to improve shared situational awareness in human-robot teaming. Let's say we've got a human team trying to perform a task in an uncertain environment, and they want to improve their performance by adding a robot teammate who can help them explore that environment and collapse its uncertainty. This is tricky in practice because in these types of environments, plans are inherently unpredictable and constantly changing. Optimal performance can't be achieved without coordinated adaptive plans. And this type of coordination requires shared situational awareness between human and robot teammates, which is wholly dependent on live and efficient communication between agents. This inspired our question: how should autonomous systems communicate with human teammates in time-sensitive, uncertain environments? One technique we can leverage is explainable AI. There's plenty of evidence from prior work showing that providing insight into the robot's decision-making leads to improved situational awareness. Additionally, XAI can help reconcile models between human and robot agents when there's a mismatch in expectation, and foster appropriate levels of trust and reliance in the system over time. Another key insight is that these partially observable domains involve communicating data that is complex, evolving, and re-referenced frequently. These factors suggest the data is best presented visually rather than verbally in order to maximize comprehension by the human teammate. Specifically, we can leverage new hardware in the form of augmented reality headsets like the HoloLens 2 to show these visualizations directly in environmental context, without incurring the costs of frequent context switching to separate devices in order to receive and parse information. One idea is to use the headset to show action recommendations, like directions on Google Maps. Unfortunately, this alone is likely insufficient. Once humans have observed such a system performing reliably, they have a tendency to overtrust that system and become complacent, being easily led astray when the guidance fails. We hypothesize that combining guidance with contextual information about how it was generated would help to mitigate those negative effects. The core contribution of this work is threefold. We first present a novel multi-agent planning algorithm for use in partially observable environments, which simultaneously controls autonomous agents and provides proactive visual recommendations to human agents. We also introduce two modalities of augmented reality-based visual guidance: prescriptive guidance, or directly recommending actions, and descriptive guidance, visualizing latent state features to aid in decision-making. Lastly, we evaluated and compared these modalities in a human subject study involving a collaborative, partially observable search task.
We'll start by describing our algorithm, MARS, a Min-Entropy algorithm for robot-supplied suggestions. MARS characterizes environmental uncertainty through the use of shared dynamically updating probability mass function, or PMF, which can be used as a reward function to solve parallel Markov decision processes and arrive at a joint policy. In our formulation, human and autonomous agents possess different goals and capabilities. These roles are codified as separate human and robot MDPs connected via shared PMF. As outputs, MARS provides both actions for autonomous agents as well as action suggestions and environment data for the human delivered via an AR headset. The robot MDP is tasked with exploring the environment, taking observations to reduce overall uncertainty. We use two types of state features: traditional world features providing state space information along with distant features that incentivizes autonomous agents to spread out their search. In a nutshell, our min-entropy formulation targets environment regions with highly uncertain PMF values, attempting to drive them towards 0 or 1 via observation. The human guidance MDP, on the other hand, has two types of actions encoded within its reward function. First are entropy minimizing exploratory actions like navigating or using sensor equipment. Next, we have goal-centric actions, where humans obtain reward if their action satisfies the goal criteria from their current state. Otherwise, they are penalized for wasting time or resources in non-critical state. Let's walk through the details of the algorithm using a search and rescue example with a human and a drone teammate exploring an environment divided into 6 by 5 grid. Onto the grid is projected a heat map representing the shared PMF. The heat map colors range from dark purple, indicating low probability, to bright yellow, indicating high probability that a grid square contains a search target. The first step is to use the initialized PMF to solve the robot MDP, for example using policy iteration or Q-learning to obtain an optimal policy. Next, we use this policy to obtain optimal actions for each robot agent and command them to take those actions. The agent or agents, in this case the drone, takes its action. In its new state, the drone takes an observation which is used to update the PMF. Here we see that the drone's current grid square has turned bright yellow, indicating the observation revealed a high target probability. This updated PMF is used to solve the human MDP, rolling out the policy to get case steps of recommended actions for the human. The action recommendations, along with the updated PMF, are sent to the human to be visualized via their AR headset. The human then uses that guidance to take their next action, which is recorded, along with the local reward the human recovered by taking that action. This reward is used to update the PMF once again. This process is repeated until all objectives have been achieved.
The AR guidance given to the human by Mars comes in two flavors, prescriptive and descriptive. Prescriptive guidance involves direct action recommendations, shown here as cyan arrows and an orange pin in the AR headset. It is characterized by an automatic System 1 style of thinking. Prescriptive guidance is easy to understand and to follow, but it leaves its decision-making process opaque. Descriptive guidance involves displaying environmental data in the form of an evolving PMF heat map. It, on the other hand, involves more effortful System 2 thinking. It acts as a decision support tool for the human, allowing them to make decisions using all available information at the cost of extra cognitive workload. By combining both guidance types, we aim to allow the human teammate to leverage both System 1 and System 2 thinking, decreasing mental load by leveraging suggestions, but deviating strategically based on environmental data when necessary. To evaluate and compare these modalities, we ran a user study where participants played a collaborative 3D AR-based game inspired by Minesweeper, alongside a virtual drone teammate helping them to defuse mines hidden in boxes. The goal of the game is to locate all 4 mines hidden throughout the grid as quickly as possible. The virtual drone can explore the grid using its noisy sensor to attempt to determine whether a box contains a hidden mine. Only the human, however, is capable of physically opening boxes to defuse each mine. The game is turn-based, with the human and drone alternating actions. Humans can move north, south, east, or west on their turn, or open a box in an attempt to defuse, progressing toward victory if the box contained a mine, and wasting time if it didn't. The experiment was within subjects, with each participant playing 1 round of the game with each of the 3 guidance types, prescriptive, descriptive, and a combination of both, filling out a short survey after each round. After the experiment, another survey consisting of ranking questions, as well as an exit interview, were administered. The experiment aimed to test 3 subjective hypotheses. We thought that participants would rate the combined guidance as both more trustworthy and interpretable compared with the other conditions. We also predicted that participants would find the combined and prescriptive conditions to be the least stressful and demanding, due to the presence of clear recommendations. For each hypothesis, we developed scales consisting of multiple Likert scale survey items taken from established questionnaires in XAI and HRI research. In terms of objective hypotheses, we predicted that the combined and descriptive conditions would lead to the fastest solve times, since participants could leverage direct guidance. Additionally, we hypothesized that participants would act with more independence, deviating from the prescribed path when given combined guidance, since they have the opportunity to take initiative when they perceive suboptimal suggestions.
For our first subjective result, trust, we found statistical significance supporting our hypothesis within the post-round and post-experimental comparative survey. We also received qualitative validation of this hypothesis from exit interviews, where participants indicated having access to both prescriptive guidance and its context helped them trust the system. Similarly, we found statistical significance supporting our interpretability measures, where participants indicated the combined guidance to be the most interpretable and helpful for decision making among all conditions. The second quote shown here highlights the value of having contextual information in order to evaluate the quality of recommendations given. Surprisingly, for our mental load measure, we found that participants in fact found the prescriptive guidance to be more cognitively taxing than the other conditions, an effect that contradicts our original hypothesis. When we looked to the exit interviews to see why, we found that the people got easily frustrated and confused whenever the system made abrupt changes in its guidance. This highlights the importance of having explanations or contextual information available to reason about why a system has behaved unexpectedly. For the objective results, we found that the participants did indeed solve the task faster in the combined and prescriptive conditions, as the heat map condition was associated with higher decision making time. For our independence hypothesis, we showed that participants deviated more from the path in the combined condition. We also showed that deviating from the prescribed path was correlated with degraded performance in the prescriptive guidance condition, but not in combined condition. This indicates that participants can take independent actions without taking a performance hit by leveraging the provided descriptive guidance to inform decision making. The interview responses paint a similar picture. Participants found that the prescriptive guidance limited their autonomy, while combined guidance allowed them to act independently and deviate from the system recommendations if they found them suboptimal. To summarize, in this work, we developed a min-entropy algorithm for robot-supplied suggestions for multi-agent collaboration under uncertainty. We introduced two AR-based visual guidance modalities for communicating environmental uncertainty and providing actionable recommendations to human teammates. And we showed that providing visual insights alongside robot suggestions improves trust, interpretability, and performance and makes human collaborators more independent. We'd like to thank our sponsor, the Army Research Lab, for funding this research. Please feel free to reach out to us if you have any questions.